Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to the second lecture of our week number 7, where we are talking about the measurement of force and torque. Now in the previous lecture you are introduced to the concept of the unit of mass. Actually all of you know from very childhood days that the SI unit of mass is kg, but we spent a major time discussing in the previous lecture about the new way of defining the magnitude of 1 kg or the value of 1 kg, because in earlier days, even when we recorded the very first lecture of this particular course, the measurement standard used to be IPK, but very recently, just about 2-3 months back, there is a change in the way we define the value of kg, and now it is not based upon the mass of any particular physical unit or physical quantity, rather it has now been related to an universal constant, which is a Planck's constant, and accordingly we have to modify all relevant definitions where we need to make use of the value of kg to define any of the derived parameters. Now after that definition we discussed about a few common ways of measuring force. Generally force measurement is always related to the measurement of mass, or I should say the measurement of weight, because weight itself is a kind of force, and most of the force measuring device actually can also be viewed a way of measuring weight of some physical quantity. So we have discussed about the mechanical weighing systems, elastic load cells, and a few other ways of measuring force as well. Today to start with, we shall be going back to the analytical balance once more, because in the previous lecture we introduced you to the concept of this analytical balance or similar kind of other mechanical weighing systems, and we discussed about different issues that the operator need to be careful about, like the effect of possible effect of buoyancy, etc. However, we have not done too much of mathematics, or we have not focused too much on deriving corresponding relations. Though most of them are quite obvious, but still today let us spend a bit of time in deriving those relations to start with. So the first in line is the analytical balance, and which is also quite often called the equal arm analytical balance, because this is the one where we commonly have one fulcrum or pivot located exactly at the center, and on equal distance from that fulcrum we have two arms or two plates on either sides, or you can say two trays. One of the tray generally houses the mass for which we want to measure the value, or the quantity for which we want to measure the force, and the other one where we put some kind of known or standard masses, and by once we achieve the balance at the fulcrum, we can easily equate both of them. Like shown here, this O refers to the position of the fulcrum that we are talking about, and here we have a W1 force acting on one side and W2 acting on the other side of the balance arm. Here the point of application of both these forces are at equal distance from that point O, which is this L. So then corresponding to this W1, how much is the moment that is acting at point O? So that moment corresponding to W1, if we call that M1, that should be equal to W1 into L. And what should be the direction of this? Look at this force W1 and also look at the position O. We can clearly see that the force will be acting in this particular direction, that is a clockwise force. Similarly, if we calculate the moment corresponding to the force W2, then M2 will be equal to W2 into L, and this force will be a counterclockwise, or it will produce a counterclockwise moment. When as L is equal, or the distance of point of application of both the forces are equal from this point O, so the values of W1 and W2 will decide the net moment or net torque that is acting on point O, and in this case that is equal to W1 minus W2 into L, or I have mentioned as W1 differs W2, or we are talking about basically the difference between W1 and W2. Depending on which one is larger, we shall be having a net moment acting at O. And then let us say W1 is the one for which we want to measure the value of the force. So, this is the one that is our measurement, and here we keep on adding more and more standard mass if W1 is larger than W2, and we keep on increasing the value of this W2 till this quantity approaches 0, that is I should say W1 approaches W2, and then we can directly equate the value of W2 to W1. And other way, like shown in this particular diagram, instead of trying to equate them, we can also get it from a scale like this. Means generally analytical balance operate based on the null principle, that is if this particular when there is an initial deflection, that is W2 is equal to 0, and we have only put the W1 into this, say this refers to this null position on the 0 position on the scale, then we can see there is a big deflection, this much of deflection that has taken place. And now our objective is to increase the value of W2 and then get this thing back to its initial null position. This actually the way I have shown it should be opposite, means let us say this is equal to 0 and then initial deflection, then talking about this particular one, and by keeping on increasing the value of W2, that is from the initial 0 level, we keep on adding more and more standard masses to W2, so that this pointer can come back to this initial null position, and thereby restoring the balance and providing a way of measuring W1. This is something that all of you know this. Let us now try to extend this principle to the balances where the arm lengths are actually not equal, because there are several situations where we may have to deal with balances with non-equal or unequal arms, just like the one shown here. Here this is generally used when you are looking for very large mass measurement. So, here the mass will be put in somewhere here, and you will be equating this by adding some mass on this particular scale somewhere here, and here the length of both the arms are not at all equal to each other. Generally we can represent them with a schematic representation like this. So, here this is your fulcrum which houses the pointer which is connected to some kind of scale, the scale will be mounted somewhere here. Now, the test mass or the mass for which you want to measure the force is connected to this particular point, that is it is acting at a distance E from this particular knife edge or fulcrum. This particular arm, corresponding arm length, is generally called the load arm. Whereas on the other side we have the power arm, and at the end of this power arm we are putting this known force, generally by adding standard masses, and the length of this power arm in this particular case is B. Then how can we write a balance equation so that we can get a relation between this Ft and Fg? Remember, Fg is the known mass, Ft is the one which we are trying to calculate, or the value of Ft, the force, that is the one that we are trying to calculate. So, how much is the force or moment rather this Ft is producing, Ft is imposing at this particular point? That is very easily can calculate that to be Ft into A, and the direction of this one will be this clockwise. Correspondingly, a counterclockwise moment will be created by Fg, and when they achieve the null position, then these two should be equal to each other. So, from there we can write Ft is equal to Fg into B upon A. That means this particular ratio B upon A is very important about the range of value of this Ft that we can measure with this. For example, suppose if your B by A is equal to 5, then what we have? We have Ft upon Fg is equal to 5. That is, if Fg corresponds to a mass of 1 kg, which actually will lead to how much force 1 kg of mass will lead to? This is of course equal to m into g, that is 1 into 9.81, that is 9.81 Newton. So, just by adding a mass of 1 kg which will lead to a 9.81 Newton of force, then we can get a measurement of Ft equal to 5 into 9.81, correspondingly whatever value you will be getting, this much of force can be measured. And this way, if we keep on increasing the value of this B by A, or keep on increasing the ratio B by A, let us say if we make it 10, then easily we can measure 10 times larger force, that is 98.1 Newton force can be measured. Or in a way, if we, instead of writing in terms of Newton, if we write in terms of mass, whatever Fg amount of force that we can measure using Ft, we can measure this many times larger mass using this. So, when you are looking for very large quantity of force measurement, that is, we are dealing with a very large value of this Ft, we can actually this particular point is flexible. We can move this particular point along this particular scale in either left or right direction, thereby changing this ratio B by A as per our requirement, and we can get quite large range of Ft to deal with. Commonly B by A is greater than 1, significantly greater than 1, but if situation requires, sometimes we can also make it less than 1, thereby allowing some standard masses to measure much lower value of force. So, this way non-equilibrium the balances with non-equal arm lengths can provide us measurement over quite wide range of forces. And then another very common type of mechanical weighing system, that is a platform balance, something I mentioned in the previous lecture also, something you very commonly find in the shops or markets, where actually none of the arms are visible. Here we just have a platform on which we put the quantity which you want to measure somewhere here, and generally in digital mode we get the output somewhere here. Now, then how this one operates? It is not an equal arm system, not a non-equal arm system. Actually, this is not an analytical balance at all. It actually operates on the principle of multiple levers. So, if we get a schematic representation of this, generally we will get a situation like this, where this is the one that you have kept on the platform. This is the platform. This platform basically refers to this one, and here you have kept this force W. W refers to the mass, or the force corresponding to the mass, or the weight corresponding to the mass which you have kept on top of the platform. Here on the instrument side, we generally use two different weights. One is this poise weight and other is the pan weight. Poise weight Wp and pan weight Ws. We generally keep on adjusting both of them, and accordingly we get a balance. Generally Wp during a particular measurement, Wp is kept constant and Ws is kept on varying. When this is not at all subject to any kind of force, Ws is 0, and the situation needs to be, or rather the device needs to be kept in balance by using a counterpoise, that is something equal to the value of Wp. But as soon as we have put this W on the platform, then we have to keep on adding something to this Ws to restore the balance. Now, for the situation shown here, if we first take a balance with respect to this particular thing, then what we are getting? We are getting Wp into B is equal to Ws into A by looking at this. And similarly, if we take another balance corresponding to this particular one, actually I have written it wrongly, how it can be. So, in Wp does not come into the picture, rather if we take a balance corresponding to this, we have Ws into A which is imposing a torque in this particular direction, and the tension which is acting here on this, that is imposing a torque in this direction. So, this should be T into B, thereby giving T is equal to Ws into A upon B. Now, focus on the platform and let us take a moment corresponding to this one. This weight W can be considered to comprise of two parts, one is W1, other is W2. W1 plus W2 gives equal to W, and their value can be anything, or the way we divide this W into two parts can be our choice. So, now if we take another moment balance corresponding to this, then we have T into C on one side, this should be equal to W1 into F upon D into E, looking at this picture, and contribution coming from W2 is just W2 into H is this particular distance. So, or T is equal to W1 upon C into F by D into E plus W2 into H. Now, the values of all these lengths, that is F, D, E, C, etc., these are our choices. So, commonly we design this lever based systems or multiple lever system such that we have F by D is equal to H by E, or F by D into E is equal to H. So, if we put it back here, actually I missed an H here. So, we have 1 by C into W1 into H plus W2 into H, that is W into H upon C. Just look at here the final relation what we are getting. If we can ensure this particular condition, then the division of W1 and W2 does not matter. Ultimately what we are getting back is the original value of W itself. And now we equate these two equations. Let us say this is equation number 1 and this is our equation number 2. So, if we equate the value of this tension T between these two equations, then we have Ws into A upon B is equal to W into H upon C, or W equal to Ws into AC upon BH, or commonly written as R into Ws, where this R is nothing but what we originally had in the bracket, AC upon BH, that is a term comprising of all these 4 lengths A, B, C and H. This is sometimes called the scale multiplication factor or scale multiplication ratio. So, again by adjusting the values of all these A, B, C and H, we can keep on varying this value of R, and once for a given system if we know the value of R, then we can easily adjust the value of Ws to get the system back into balance and then get the corresponding value of W. Finally, look at here. Again in this case also W upon Ws is equal to R. So, if we make R a large value, like say if we have R equal to 10, then this W can be 10 times larger than Ws. Similarly, we can also go for much smaller measurement as well using this. So, this is a platform lever system, or I should say a multiple lever system in the form of a platform balance. Similarly, we can also have a few other kinds of multiple lever systems as well used for common mass measurements. So, these are the common types of mechanical weighing systems which we mentioned in the previous lecture, and little bit more information about them in today's lecture. With this, let us move to a few other kinds of force measuring system. This is another one, a very important one actually, which is called the proving ring. Proving ring, truly speaking, is a kind of elastic transducer or elastic load cell, something again which we have discussed in the last class, but this is a very common device, a very popular one and a very important one as well. Here as you can see, it is nothing but a ring, but with something in between. Look at any one of them. You can say if we take the smallest one. So, here you have this ring, but inside the ring you have something there. The idea of this one is that the ring of some known dimensions will be subjected to some kind of force at these two ends. The way I have shown, this is actually compressive force or compressive force, but proving rings can be used for both tensile and compressive stress measurement or force measurement. As we are putting some kind of force, tensile or compressive, whatever it may be, that will cause some kind of deformation or deflection in the diameter of this ring. Our objective is to measure that change in diameter of the ring, and whatever machinery or instrument that you can see inside, the purpose there is solely to measure the change in this particular diameter. So, we can have both kind of situation. When it is subjected to some kind of compressive load, there will be a reduction in the length or diameter. Similarly, when it is being subjected to some kind of tensile load, there will be an increase in the diameter. And now we can have some kind of instrument here which will measure this change in length. We can have any kind of length measuring instruments, like 2 weeks back the kind of instruments that you have learned for measurement of displacement or deflection, anything can be used here. Commonly we can have a micrometer, basically a microscope based instrument, or we can also have LVDT, which can give us information about very small deflection. LVDT being a quite common choice if we are looking for quite accurate proving ring and something of high accuracy. Proving rings are available at wide range of sizes, like the picture I have shown here. There you can see there are 4 proving rings, and each of them are having different diameters. Similarly, we can design them with any possible dimensions. Each of them have their own ranges of forces, and accordingly we can get a quite wide range of force measurement. The design of proving ring generally is governed by the guidelines set by the National Bureau of Standards in 1946. National Bureau of Standards in US that sets the standard. Actually, you will not find this name now. It is presently called the NIST, National Institute of Science and Technology, which is one of the leading global bodies to set up the standards, primary standards. So, based upon the guidelines they set up in 1946, proving rings are still designed. Here idea is very similar to any kind of elastic transducers. There we have seen that for any elastic transducers we generally get a relation of F equal to Ky, where K is the corresponding deflection constant for the transducer, F is the force which we are trying to measure, and Y is the deflection. Now, in the last class we have discussed about a few possible kinds of design of elastic transducers and corresponding expressions for K. Something I intentionally left down there, that was a ring. When we are dealing with a ring of a shape like this, a ring having a diameter of d. Let us say the thickness of the ring is t. If this thickness is extremely small compared to the value of d, then the expression for k is something called the thin ring approximation, is a very standard one, 16 upon pi by 2 minus 4 minus pi into EI by d cube, where E is the Young's modulus, I is the moment of inertia for the ring, and d is this outer diameter. Of course, the thickness, I repeat, has to be extremely small. Now, it has been proved by Timoshenko and a few others that even if the thickness is, if it is a bit significant, still we can keep on using this thin ring approximation relation even for thicker rings as well, without introducing too much error. Even for quite significant thickness or rings with quite significant thickness, generally the thin ring approximation is found to provide less than 2% error, and that is why we are going to continue with this relation. So, if you continue with this, then the expression for your force is going to be 16 upon pi by 2 minus 4 upon pi into EI by d cube into y. So, the object our task reduces to the measurement of the value of this y, which is the deflection, because everything else are constant. E depends upon the value of the depends upon the material that you are using. D and I both depends on the design and generally provided by the manufacturer itself, or in a way this entire thing comes as a constant. I should not say R because I was already using K. So, this K generally already comes from the manufacturer. Just by measurement of Y we can get the value of this corresponding force or F. And if we are looking for an LVDT kind of measurement, then this alone is sufficient. Sometimes instead of measuring this way, we go for the measurement of the angle of deflection. That is, if this is the original shape, I am trying to draw a circle actually, but it is ending up with something quite odd shape. Let us assume this is the initial shape. So, these are the primary dimensions. Now, if there is a deflection of this one and the deflection is measured in terms of an angle phi, then the corresponding bending moment can be related as is equal to PR by 2 into cos phi minus 2 upon pi, where R is the radius of this particular circle, initial radius, P is the oh sorry, I have written both to be R, it should be P. P is the pressure that is acting on this, and m is the corresponding bending moment. From there also we can easily calculate the deflection just by measurement of the value of this phi. So, proving ring is another quite common type of elastic transducers used for measurement of large forces. Let us move to the next one, piezoelectric load cell. Okay. While the mechanical weighing systems, proving rings etc. are classical devices, age old devices, this is something much more modern. The principle of piezoelectricity we have briefly touched upon while we talked about the displacement measurement, the same principle coming back here. There are certain natural crystals and certain artificial materials which when subjected to some kind of force produces certain charge. Actually, without going into too much detail, what happens that initially the positive and negative ions are uniformly distributed over the entire crystal body, but when they are subjected to certain kind of stress, compressive or tensile, certain kind of force or pressure, then they distribute themselves such that one side develops a net negative potential, other side develops a net positive potential, and thereby it is possible to get some kind of flow of charge if we connect them by an external circuit like this. That is, one side of the plate becomes positive, other side of the plate has become negative, and now we are collecting them by an external circuit, and that gives some kind of voltage output or some potential difference. And this potential difference, if we measure properly, can be found to be related to this force or directly related to this force. So, I have mentioned there, I can clearly remember that piezoelectricity is a very modern and important branch of measurement, and lots of research are going on in this particular line, and commercial devices are also available, simply because this is extremely advantageous from several contexts. Of course, there are certain natural material like DNA can be a very important example, and several crystals also which produces or shows piezoelectricity, but generally we keep on using synthetic materials, and these are certain common synthetic materials. Again, this table I have already shown there, I have just taken the synthetic part of that table. PGT, that is lead zirconate titanate, is probably the most common material, but barium or lead titanates are also used in piezoelectric devices. Now, the biggest advantage that we get with piezoelectric load cells is charge being directly proportional to the force. So, we of course, we need some kind of mathematical relation for this, but generally that is provided by the manufacturer, and therefore, once we measure this charge in by the means of the external circuitry, we can directly get the value of the force. And other big advantage with piezoelectric load cells are the output independent of the size of the sensor. That is, the size of the crystal does not limit the amount of force that can be measured with this. Even with a very small size crystals, we can get the measurement of very large forces, and therefore, we can comfortably attach the load cells to any kind of specimen depending on whatever kind of contour that we have on the surface that we are dealing with, we can get the measurement. Then wide range of operation, as I just mentioned, it is generally showing excellent kind of frequency response for any kind of transient input. Therefore, we can easily use this piezoelectric load cells, particularly for dynamic measurement, or I should say they are very suitable for dynamic measurements or dynamic force measurement, mainly because of this excellent frequency response, because the response times are quite small, and they hardly have any kind of amplitude distortion or phase distortion. High resolution is again a very desirable characteristics. High stiffness or rigidity, once the force is removed, the cells are generally able to recover back their original shape, thereby allowing or being ready for another measurement. And again, another quality very much desirable for dynamic measurement, because as the force keeps on changing with time, the cell is able to adjust immediately and provide the corresponding output. And minimal influence on the structure, because of their small size and high stiffness, they hardly affect the surface on which we are putting them. Their maintenance costs are quite low. So, all these are very much advantageous features. But there are a few other issues also that we have to consider. One big issue with piezoelectric load cells is they are prone to drift. That is, if we subject such kind of load cells to some kind of constant force, then if we say plot the time on one side and the output on the other side in the form of voltage or charge whatever, they generally they are not able to maintain a constant level of output. Our desirable situation is something like this, that is a constant voltage with time, but they generally show some kind of drift, that is the output keeps on changing with time. That is because nature does not tolerate any kind of imbalance, or rather nature always tries to get back to the situation of balance, so that no unbalanced potential are left. Accordingly, the charges always find some way of readjusting themselves, so that they can go back to the situation of balance or system of balance inside the crystal body itself, and that provides this drift or leads to this drift. That is why we generally have quite short time to take the measurement, and also they are not at all preferable for static measurement, again precisely for this particular phenomenon. However, if we can somehow provide some kind of output measuring device which has a very good response time, that is in a very short interval we can get the reading, then we can get some idea about the static measurement. But if we are looking for some kind of application where our objective is to ensure that the force value remains constant over a long period of time, then this is not the device to use. We have to find some other device. This is particularly suitable for dynamic load measurement. Another issues can be if it can pick up stray voltages from the wires, and it will be very difficult to separate that out from the final output, because in the output level there is no difference between that. And if the crystal they may be quite delicate, so if they are subjected to over pressure, they may crack or deform, and prolonged use at high temperature must be avoided, because they may show some kind of mechanical deformation when they are subjected to high temperatures for long duration of time. Despite these problems, piezoelectric load cells are here to stay, and they are probably the most suitable device among all the ones that we have discussed so far for dynamic force measurement. Next one, another very important device, vibrating wire transducers. It is just a wire. We have an wire which is connected to or which is being taught at two different ends. This is one end, this is another end, and the force has been connected to these two ends, and they are fixed. Now, among these two anchors, generally one of them is fixed. You may think about, say this is the fixed one, and the other one, the other anchor, that is this one, this is able to move. As this one is so, when this second anchor is subjected to some kind of force, there will be a change in the length of this, or whenever this is being subjected to some kind of tension, if both the anchors are fixed, then there will be a change in the natural frequency of this particular wire. Or we can visualize the other way also, like suppose if this anchors is being subjected to a force, then the wire will start to oscillate or fluctuate with its own natural frequency, which we can represent as omega is equal to 1 by 2 L √ f by m. Here m refers to the mass of wire per unit length of this, that is this m is having an unit of kg per meter, f is the force which we are trying to measure. So, if we know the value of this omega, then easily we can calculate the value of this force, and to know this natural frequency, we generally have some kind of excitation coil, some magnetic field which tries to pick up this oscillation and provides a way of measuring the value of this omega. These vibrating wire transducers can operate in two modes. One is a damped mode, where the wire is allowed to freely vibrate when that is being subjected to a pulsed excitation, that is there is a force application for a small instance of time, and then there is no force, but the wire keeps on vibrating freely with its own natural frequency. The frequency of the damped free vibration is measured. It is the older of the modes and in use since 1930s. The second one came around 1960s, which is called the sustained mode. The wire continuously excited at resonant frequency, and now we need two coils. One coil continuously excites the wire, and the other one measures the frequency of vibration. The resonant frequency among these two modes actually has found to be a bit different, particularly the resonant frequency in the sustained mode. Generally it is called that the resonant frequency is depending on the length and material and diameter etc. of the wire, but that has not been found to be true always, because the resonant frequency among these two modes, the damped mode and the sustained mode, has been found to be little bit different. There is about 0.1 to 0.3% difference. So, if you are looking for very high accuracy, generally this is the level of accuracy that we also expect from our device. So, it has to be, must be very careful in which mode we are working with, and should use the corresponding value of resonant frequency to avoid any kind of error. They are again quite accurate device if we can measure them properly or measure the frequency properly. There are certain issues, like they are generally temperature sensitive. The wire itself, being conductive in nature, can be very sensitive to temperature, and the non-linearity of the output is another concern. Here omega and f does not have a linear relationship, or rather if we express this one in terms of the force, what we are getting? We are having 2L omega whole square is equal to f upon m, that is f is equal to 4m L square omega square. So, f and omega are actually having a quadratic relationship and not a linear one. So, this non-linearity of the output also needs to be very careful, we have to be very careful about while taking the output measurement. But these vibrating wire transducers are particularly suitable in permanent structures, like for measurement of deformation or crack generation in structures, like just shown here. Say we already have a crack, we know there is a crack somewhere in the structure, and we want to see whether the crack is keeping on developing or just remains the same. Then we can attach a vibrating wire transducers like this, where two anchors are fixed to two different sides of the crack, and now if there is a change, means if the crack widens, then there will be a change in the distance or change in distance between these two anchors, thereby changing the tension on this particular crack, this particular wire. Accordingly, there will be a change in its natural frequency, and if we can measure that, then we can get an idea about this change in the length of the crack. This kind of things are quite often welded inside the reinforced concretes or steels to measure their corresponding stresses. Another quite new application that I have seen, where here the vibrating wire transducer has been mounted or housed at the base of a river, and there are single or multiple liquid reservoirs on top of this, and here objective is to measure the height of the column of liquid on top of this. Now, if there is a change in the height of this if there is a change in the height of this liquid column, corresponding force acting on the transducer will also change, and from this corresponding response we can get both the ideas, whether whether there is any change in the water level, or if the water level is same, then whether there is a change in the position of this earth crust, that also we can measure from this. So, these are certain quite interesting examples of the application of vibrating wire transducers. Next, something most common I mentioned in the previous lecture also, hydraulic load cells. Very simpler operation. We are applying a force on some platform, on the other side of the platform we have a liquid filled cavity. So, the force is being transferred to this diaphragm, and thereby causing an increase in the pressure on the diaphragm, and this increase in pressure is sensed by a pressure measuring device, a Bourdon gauge or any kind of common pressure measuring tool. Pressure gauges we shall be learning just in the next week only, but the application is very simple, because whatever force the upper plate is being subjected to, that will easily be transmitted to this lower diaphragm, and they are directly proportional to each other. So, we can get a direct measurement of the force that is acting on the diaphragm. Hydraulic load cells are very common in industrial applications and also in several common force measurement applications. And next is pneumatic load cell. Operating principle is quite similar, but instead of a liquid we are using a gas. Now, have you seen this particular picture earlier? I have intentionally put the same picture here. This is the nozzle flapper transducer, which you are introduced to during the displacement measurement, and the operating principle is very same here. Here on just for repetition, here we have a big tank which is maintained at a constant pressure of PS, and the gas is there. Now, the gas is allowed to pass through a fixed restriction here, So, we have this nozzle. On one side we are having the gas coming through from a tank maintained at a pressure PS and fixed restriction, and the other end of the nozzle we have this flapper. This flapper is being subjected to, or it is connected to the location where you want to measure the force. So, whenever there is some force applied on the flapper plate, the flapper moves, thereby changing this opening. This x refers to the distance of the flapper, this x refers to the distance of the flapper to this nozzle opening, and so on application of the force the value of x changes, thereby modifying the delivery pressure, and accordingly the mass of gas stored in this measurement chamber that keeps on changing, thereby changing the pressure in this measurement chamber itself. And by measuring the pressure in this measurement chamber, we can easily measure the, or easily get an idea about the force that is acting on this on the flapper plate or the displacement, whichever we would like to measure. Do you remember the operating principle? Let me very briefly repeat this one. Let us say GS is the, let me remove all this marking first. Let us say GS is the mass that is coming from the tank and Gn is the mass that is going out to the nozzle. So, under steady state operation, Gs 0 will be equal to Gn 0, which refers to steady state, and so total mass in the measurement chamber that remains constant. Let us say corresponding mass in the measurement chamber is m 0. Now, if there is a change in the position of the flapper plate because of some force application on this, then let us say Gs is the mass flow rate that is coming through the restriction, and Gn is the one that is going through the nozzle outlet. If they are not equal, then there will be some mass accumulation. So, the rate of change of mass stored in this measurement chamber can be given by this. This Gs is generally a function of this tank pressure P naught itself only, and now P naught can be written as P 0 0, which is the initial steady state value, plus delta P naught, which is a change in this pressure of this, and so we can write this as Gs naught plus the higher order terms, that is Ks into delta P 0. Similarly, the Gn depends upon both this P naught and x, on both, or let us say xi. So, Gn can be expanded like this. Let us say x 0 is the initial position. So, correspondingly we are going to get Gn 0 plus this exercise we have done earlier. I am just doing it very quickly for a recap. This can be written as Kn plus Kn(x) delta x naught. Actually forgotten exactly what notations we have used, but these are the common notations. So, if we come back to the original equation, your dm dt can be now written as K is delta P 0, which is coming from the first equation, delta P 0 plus Kn(x) delta x 0. We are neglecting of course all the terms from second order onwards, that is, sorry, this symbol should be negative. So, Ks minus Knp into delta P 0 commonly we use the ideal gas approximation for this, and if we use the ideal gas approximation and use the relation, that is Pv equal to mRT on this gas stored in the chamber, then it can be shown that this relation finally reduces to something like this. where a very much first order relation, where the time constant tau comes out to be volume of the tank divided by this R T0 into Kn minus Kn and K comes out to be minus of Kn by Kn minus Kn. This derivation we have done in that week itself. This is a repeat of that, but still for the sake of continuity I have done the entire derivation once more. So, this relation actually provides us a way of measuring the value of this delta x, or for a given delta x we can get a measurement of this delta p. So, if we measure the delta p, we can correspondingly measure the delta x itself, but the same way we can also modify this delta x in terms of force and we can get a measurement of the force. So, the delta p, that is the change in the pressure in this measurement chamber, this one can be calibrated either in terms of the delta x, that is in terms of the change in position of this flapper plate, or in terms of F, which is the force that is this flapper plate being subjected to. We can calibrate this one in terms of either of them depending upon what is our objective, and accordingly we can use the same device either as a displacement measurement one or a force measurement one, operating principle remaining the same. So, any pneumatic load cell operates very much the same way. So, this takes us towards the end of our discussion on force measurement. We shall very quickly be discussing a bit about the measurement of torque to finish up on this particular chapter. Now, what is a torque? I am sure all of you know even from your high school level physics that torque refers to a force which leads to rotational motion, just like the shown here, that is on the application of the force at this particular position, instead of a linear motion we can get an angular rotation. So, this is the way we can calculate the direction of torque. Quite often we can relate this one to a left hand thumb rule kind of situation or whatever, like if we place, quite similar to what we do in electricals, if we place these three fingers of your left arm perpendicular to each other, then if the index gives you the direction of the force and the middle finger gives you the direction of the distance, then thumb is going to give you the direction of the torque. Or sometimes we can also relate them by something like this: if your force is acting in this direction and then the depending on whatever way you are looking at the force, or if you are standing at the point with respect to which you want to measure the torque, then whether you are looking in clockwise direction or anti-clockwise direction to find the force, accordingly also we can decide the direction of the torque. Now, from your vector algebra you have learned quite a bit about torque measurements, or I should not measurement, I should say the properties of the torque. Again, a very quick recap, just what we have discussed a while back about the analytical balance. Say when your the fulcrum is being subjected to L1 and L2, the two equal torques, then both of them are equal, then it will remain in a place of balance and you shall be having an equilibrium, so that you have T net to be equal to 0. So, thereby null position is restored. However, if one of them is larger, like in this case T2 is larger than T1, so there is a net external torque and you are into a non-equilibrium location. So, then the object will be experience an angular acceleration. Like we have started this particular chapter by referring to Newton's second law of motion, where we have force is equal to mass into acceleration. We can easily convert this one to corresponding torque relation, that is T is equal to I omega, where I is the moment of inertia, omega is the angular deflection and T refers to the torque for this. Now, for the measurement of torque, actually torque measurement is quite commonly related to the measurement of power, because whenever you are talking about something, a shaft may be rotating with a speed, then with a particular RPM, then and a torque is applied on this, we can easily relate the torque and its angular velocity with the power with which we can get from this shaft if we are talking about a power producing device, or how much power the shaft is absorbing if you are talking about a power absorbing device. So, whatever we are going to talk about regarding the measurement of torque, they are all applicable to the measurement of shaft power. So, dynamometer is the term that is used for any device that is commonly used for the measurement of torque. Now, dynamometers can be commonly of three types. One is the absorption dynamometer, the most common type, where the entire power that the dynamometer receives, they are dissipated to the surrounding or to some other device, or I should not say to the other device, that the entire power is being dissipated. That is the mechanical energy that dynamometer is receiving from the source, it does not supply it to some downstream device, everything is dissipated. So, therefore, these absorption type dynamometers are commonly connected to power producing devices like engines or motors. Examples can be mechanical brake systems, hydraulic or fluid friction brakes, eddy current dynamometer. Mechanical brake, the oldest examples can be the rope brake or prony brake system. You can relate this one, just the term brake is there, you can relate this one to any brake of your vehicle. What we do during the braking is just the way an absorption type dynamometer works, means the entire power the engine is producing on applying the brake, we are dissipating the entire power in the form of friction, thereby reducing the velocity of the vehicle to 0 during the braking operation. The second kind of dynamometer is the driving dynamometer. Here it measures power and or torque and also supplies energy to drive some kind of downstream device. So, they are suitable for driven machinery like the pumps or compressors. Common examples can be torsion and belt type dynamometer, epicyclic train dynamometer or strain gauge dynamometer. There is a third kind also called the transmission dynamometer. They are more like passive devices. They are placed at appropriate location within a machine or between two neighboring machines to sense the torque precisely at that particular location. It does not dissipate the power, thereby causing no subtraction in the value of the power, but they also not add anything. So, the magnitude of the power therefore generally does not change too much. Common example can be electric cradle dynamometer. We shall quickly be discussing only about a few types of absorption dynamometers here, just to give you some idea about how they work. So, we have the rope and prony brake dynamometers first. The one shown here is a schematic of a rope brake dynamometer. Here a rope is wrapped around this particular drum or maybe a shaft. On one side you have a spring balance, on the other side you have this weight, and whatever force or power this rope is receiving, because it is or rather whenever the rope is being wrapped on the shaft, it absorbs entire power in the form of friction, and the corresponding brake power can be related to this particular from pi d n to W by 60, or I should say it should be n by 60, because capital N generally refers to RPM. So, n by 60 refers to RPS, revolutions per unit second. So, pi d n gives you the distance, angular distance travelled, and W is the corresponding counterweight, S is the value on the spring balance, and their difference multiplied by pi d n by 60 gives the brake power. This is a very simple way of torque measurement. They are cheap, very old way of torque measurement, and therefore very simple, can be constructed very quickly because you hardly need any device for this, just a suitable rope, one spring balance and some counterweight, and with suitable connection between them, and you are done with. But the problem is the friction coefficient. As the rope is absorbing, particularly when the capital N is large, that is the RPM is quite large, then a large amount of power needs to get dissipated in the form of friction. So, it can increase the temperature of the rope quite significantly, and therefore, we need to provide some kind of cooling option. This is the cooling channel which must act to keep the rope temperature within certain range, because one problem is the rope may suffer some kind of damage because of the elevated temperature levels. Second issue is that the friction coefficient keeps on varying with temperature. So, it becomes difficult to get a measure about the torque value or the brake power value if the temperature fluctuates quite a bit. And the other variation of this one is a prony brake. In case of a Prony brake, we have two brake blocks, generally wooden blocks, one here, another one there. By suitable application of these nuts and bolts, we can apply them on top of this flywheel or shaft. Generally, we have an helical springs located somewhere here between the upper block and the flywheel, to control the speed at which the brake is being applied on this. And then we have the torque arm, the lever based systems on which we are putting this weight. So, using the value of this W, we can get a measurement about the total force, or rather total power that is getting dissipated, and also corresponding value of torque. This is the way we generally measure this one. The brake power will be 2 pi n t, again it should be n by 60. So, T is the torque, and torque is nothing but this W into L, L being the length of this torque arm, this is L. Again, this is the simplest possible design, quite similar to the rope brake. Prony brake probably goes back even more in terms of time, but very large heat dissipation or heat generation that we have to be dealing with. Next, the hydraulic dynamometer, a very common device. Here we have fluids which are being circulated over the main shaft, around the main shaft, and the power being dissipated is transmitted into the water, or the corresponding temperature, therefore, we can keep into limit. That is the working medium, which is fluid, not, I should not say it is water, it can be some kind of oils also, that also act as the cooling medium. That is, it serves a double purpose, both as the working medium and also as the cooling medium. So, it employs fluid friction, which is always better to work with compared to solid friction, like in case of rope or Prony brakes. The heat carried by the fluid itself, so no separate cooling arrangement required, and the output power can easily be controlled by mounting a few sluice gates, thereby controlling the flow of the fluid around the shaft. And the final device to talk about is the eddy current dynamometer, where you have a stator part, you have a rotor part, and just the way any common generator works, eddy current dynamometer works the same way. As the magnetic field is there, as the power is applied, it produces a voltage output, and that from that voltage output we can get a measurement of this corresponding torque. Eddy current dynamometer probably is or it definitely is the most popular one among all the absorption type of dynamometers, and a very common instrument for torque measurement, because it offers huge set of advantages like high brake power per unit weight. It uses less than 1% of total power for producing that field excitation. So, there is hardly any loss in the value of power, very easily to control and operate. Just by controlling the field excitation, we can always control the operation of this dynamometer. They are smooth and can produce continuous torque over all conditions or over the entire range of operating conditions. At very low speed also they can produce relatively higher torque. No intricate rotating parts apart from the shaft bearing itself, and also no natural limit to size. That is another big advantage, that we can have eddy current dynamometers starting from very small to very large scales as well. So, these are some common devices for torque measurements. We are not going to lengthen this discussion any further, because then it will be difficult to limit this one to the scope of a class. If anyone is interested, you can search a bit more, maybe refer to some textbooks, may go to internet to find about the other kinds of dynamometer and also other types of force measuring devices. Like there can be a few other types of force measuring devices as well. There can be optical modes, there is gyroscope based load measurement, which are more like research topics, and if anyone is interested can go for it, but I am trying to limit myself more to those which are easy to understand and also have very much practical relevance. So, that takes us to the end of this chapter. So, we have here talked about the SI unit of mass, the new SI unit of mass, the common I should not say the new SI unit, I should say the new definition of the SI unit of mass. Then we have discussed about the common methods of force measurement, talking about the mechanical weighing system, analytical lever with both equal and non-equal arms, and also the platform balance system which uses multiple levers. Then we have talked about the elastic load cell, proving ring in particular, then the strain gauge load cell we have talked about in the previous lecture, Today we talked about the piezoelectric ones, the vibrating wire transducers, pneumatic and hydraulic load cells, and finally we briefly talked about the dynamometer. 4 different kinds of dynamometer we have talked about, or I should say we have talked about mostly the absorption type dynamometers like the rope and prony brake dynamometers, eddy current dynamometers, and the hydraulic dynamometers which I have talked about. So that is it for our module number 7. Please try to solve the assignments which will be which are already available with you, and next week we shall be discussing about the pressure measurement. So thank you very much.